screen. Let's share this one.
Okay.
Okay. Guess no one watching football today. Hello, 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 hello. So, let me open the tabs. Okay, today topic gonna be about. Everyone hear me well, right?
Yep.
Let me put the chat here. Okay, it's gonna be about first. It's gonna be about a tree. So let's see. Not this tree. I mean this one. Okay. Let's start from this picture, like to have understanding what is tree. You can check Richard Shaza blog. Here's the link. So
today with Zoom, please. Hello.
Yes, it's missing.
Okay. Thanks.
Is this better?
Yeah, that's great. Thank you.
Okay, so a binary tree is a fundamental data structure in computer science and software engineering. It is consistent of node where each node has at most two child nodes referred to as the left child and the right child. The topmost node in binary tree is called the root node. Binary tree have various applications in computer science, including in algorithm data storage and searching, depending on how the nodes are organized and the properties they adhere to. Binary tree can be classified into different types such as binary search tree, evil tree, and heap tree. So we have a root, we have a child, this is parents of child, this is subtree of the whole tree. We have leaf node and we have levels. So leaf node are like the last one. We have height.
Yeah.
And yeah, and the important question is like, what's the difference between binary tree and binary search tree? Wait, there is too many people here. No one watching football, guys? Wait, someone is muted. Benny, I think I met you. Maybe you had a background noise or something. Yeah, I forget too. I forget that we studied the binary tree in what is it called, in Alex. Yeah, but like this problem we're gonna see today all about tree, so this is gonna be refreshing. So what's the difference between binary tree and binary search tree? Binary tree is general tree structure where each node can have at most two nodes. There are no specific rules about the value of node in a binary tree. They can be organized in any way. So if something like this, then it is a binary tree. But binary search tree is type of binary tree that follow a specific ordering property. For each node in binary search tree, all node on its left subtree have value less than the node value on the right one. So if you notice here, 3, here it's gonna be 10. Here 1, the right's gonna be 6. So this is binary search tree. So we can keep going reading the handbook. If someone wanna check this, I post the link in chat. So a tree is widely used abstract data type that represents okay, this word I always struggle to say it.
Hierarchical.
Okay, a data type that represents a hierarchical structure with a set of connected nodes. Each node in the tree can be connected to many children, but must be connected to exactly one parent, except for the root node. Okay, which has no parents. Okay, so this is the same thing we did read in the blog. A tree is undirected. Oxamon said I can see his screen. Yes, he's sharing. Okay, you can see my screen. Like, try to stop stream and join again, or let me maybe try now. Okay, I'm sure it should be working fine. Okay, let's see how many. Okay, so other people are watching. So for a tree is undirected and connected a cyclic graph, there are no cycle or loops. Each node can be like the root node of its own subtree, making recursion a useful technique for tree traversal. For the purpose of interview, okay, so this is the important part, you will usually be asked on binary tree. You will usually be asked on binary tree as opposite to ternary tree, which have like 3 children, or an array tree. In this page, we will cover binary tree and binary search tree, which we saw here. So this is binary tree, and this is binary search tree. Okay, with this. This is very good data. Okay, thank you, Mahmoud. Tree are commonly used to represent. Okay, this word again. Let's check it out.
Hierarchical.
Hierarchical. Okay, hierarchical data. Example: file system, JSON, and HTML documents. Do check us out. Section on tree. I think this tree you're gonna see it tomorrow, I believe. Oh, the Sunday. Okay. So, which is advanced tree used for efficient storing and searching strings? Okay, so I think we all have idea about tree, right? And we saw this. Give me a second. Kevin, you have background noise. If you can like mute your mic, I will mute you like temporarily. Let me know when you mute your mic. Me, Titi, you also have mic open. Okay, let's continue. So we did see this one in this picture, I believe, but the names are a bit different. So neighbor mean parent or child of node. Neighbor. Ancestor, a node reachable by traversing its parent chain. Descendant, a node in. Okay, Pascal, your mic is open. Oh, you want to say something?
Oh, sorry. No, sorry.
Okay,
sorry,
yeah,
please.
No, if someone want to say something. Okay, Michichi, let me unmute you. 1 second. Okay, now it's good. If someone want to say something, you can talk. But just sometimes someone have mic open and the background noise. Degree. Oh, we are here. Descendant. A node in the node subtree. A degree. To say this. Degree. Number of children of a node. Okay, degree of a tree, maximum degree of node in the tree. Distance, number of edge along the shortest path between two nodes. Level, depth, number of edge along the unique path between a node and the root node. Width is number of node in the level. Okay, this is common term. We should like study them. Binary tree. Binary mean 2, so binary mean 2. So node in binary tree have maximum of 2 children. Binary tree term. Complete binary tree. A complete binary tree is binary tree in which every level except possible the last level, in which every level except possibly the last level is completely filled and all nodes in the last level are as far left as possible. Okay, complete binary tree is binary tree which every level 1, 2, 3 is completely filled. Okay, it's filled. This one is filled except the last one as far left as possible. Balanced binary tree is structure which the left and the right subtree of every node differ in height by no more than 1 node.
I think the example is dark a little bit. Yeah.
Okay, let me...
I can't see it clearly.
Okay.
Yeah.
Okay. Balanced binary tree is a tree structure in which left and right subtree of every node differ in the height by no more than 1. Okay, so if I saw tree and I can say this binary tree is balanced. Okay, someone have limiter. Maybe I can do maybe this better.
Yes.
Use the dark mode for the tech interview.
But the picture gonna stay dark, cause
okay.
So to say this balance or not, it have the right and the left subtree should not have more than 1 height. I think in this post there is more details about this. Time complexity, what is balanced binary tree. But to solve our problems today, we don't need to know like all the details, so we can like each one of us study more this later. And let's jump to like to solve problem, and we need some of this information, we can go back to them and learn. So now binary search tree, we did see it. In order traversal of binary search tree will give you will give you all elements in order. Be very familiar with the property of binary search tree and validating that binary tree is a binary search tree. This come up more often than expected. So be very familiar with the property of binary search tree and validating that a binary tree is a binary search tree. Okay, so we need to be careful with this binary search tree. When question involve a binary search tree, the interviewer is usually looking for a solution which run faster than ON. Space complexity of traversing balanced tree is OH. H is the height, I believe, where H is the height of the tree, while traversing very squid tree, which is essentially a linked list, will be ON. What is squid tree? It's not balanced, right? So this is balanced tree, this is not balanced tree. Okay. So thing to look out for during the interviewer, you should be very familiar with writing pre-order, in order, and the post-order traversal. I believe this is also you're gonna find it in the post. There's so 3 traversal order, pre-order, and post-order. So pre-order search when you go 4, 2, 1, then 3, then you come back, I believe, to 2. 1, 3. Do you come back to no, you don't come back. Okay, you finish here.
4, 2, 1, 2, 3.
3,
You go
and
back
then
to the...
you go to 6 because we finished this.
No. Mm-hmm.
Then 6, 5.
No, it's not directly to the 6. You need to go back to the root.
Go back to the first, yes.
Yeah.
To the root and then go to the 6 and 5, and back to the 6 and go to
Mm.
7.
Yeah.
This
Okay.
problem with,
So
with
this is yes, اسمح.
With more
this,
sage left, sage right.
Can you repeat, please?
this problem with the recursion. Yeah, solve with recursion, not iteration.
Okay, so like we are seeing here just like the direction of traversing the tree. So if I go from 4 to 1, 3,
Maybe
then
he back a previous level.
yeah, so like if I want to get all the value of this tree, if it is in pre-order, I'm gonna go 4 to 1. I'm gonna have this array right here: 4 to 1, 3, 6, 5, 7.
He moved to all lifts.
But notice in order, I didn't have 4 first. I did go until I found the last node, and then I added to the list. Then I come back to 2. Then I added, and then I go to the right node of it. Then I finish with this part. Then I come back to the root, and then I do the same thing to this side. Again, I go to the maximum, I believe maximum left.
Yeah, maximum left.
Then go back. So this is on order. Post order is you go from 1. Okay, so instead of going 1 and come back to the parent 2, you jump to the tree. You jump to the, what is it called? Is it sibling? I think sibling.
Sibling.
Yeah, sibling.
Or neighbor.
And then you come back to here. Okay. So this is something we need to be aware of, this tree type of traversing. And recursively, as an extension, challenge yourself by writing them in iteratively. Sometime in interview, ask candidates for an iterative approach, especially if the candidates finish writing the recursively approach too quickly. Okay, so you need to solve it in recursive, and then you need to have a plan to solve it like just with a loop. Common routine. Corner case, empty tree, single node, 2 node, a very square tree like linked list. Common routine, insert a value, delete a value. So be familiar with the following routine because mandatory question make use one or more of this routine in solution. Insert a value, delete a value, count number of node in tree, whether a value in the tree or not. Calculate the height of tree, binary search tree, determine if it is binary search tree, get maximum value, minimum value. Okay. So use technique that we're gonna use. We can use recursion is the most common approach of traversing tree. When you notice that subtree problem can be used to solve the entire problem, try using recursion. When using recursion, always remember to check for the base case, usually where the node is null. Sometimes it's possible that your recursive function needs to return 2 value. Traverse by level. When you are asked to traverse by tree level, use breadth first search. How to call this? Breadth first search. And summation of node. If the question involves summation of node along the way, be sure to check whether the node can be negative. So this is the problem we have that we're gonna try to solve, is maximum depth of binary tree, and this two. So, but before we do that, it's important to understand this technique because we're gonna use them, especially this breadth first search, and the other one called depth initial search. So I'm gonna share these documents. It have a bit like each technique explain, just to like keep it as a note. and let's try to understand them. So when we go jump to the problem, we try to see which one we can use, or maybe we combine them both. We don't know so far. So this is just a definition for binary difference. So one of the technique is recursive depth first search, and other one is BERT first search. And you can also do like iterative depth first search, which if you notice they mention it here. Sometime interviewer ask candidates for an iterative approach. Okay, I'm sorry, Shelda. Okay, I will zoom the documents 1 second. Yeah, so you notice here even if you solve it in recursive, you might get asked like, can you solve it using iterative approach? So knowing this technique is very important to like how to do it with the iterative approach. So let's see what is depth first search and what is BERT first search. First, let's see depth first search. Let me share this video. I'm gonna share the video link, right? But let's watch it together. I'm gonna share my screen. Share the Chrome tab so you can hear the audio. Application. Let me crack the volume, maybe it's gonna be.
Depth first search.
Okay, wait for everyone to join the stream. If you feel like the volume is low, you can just start the video on your end. Is here in the chat. And let's start. Let's try to understand this depth first search. Then we're gonna see what is
breadth first search.
So depth. Let's call us DFS and BFS. We're gonna understand them. Then we're gonna see what's the common difference between them. So when we jump to the problems, we're gonna feel confident that we are able to solve it. Okay, I'm gonna start.
Today, I'm going to teach you depth first search. Depth first search, or DFS, is an algorithm for...
You can hear audio? Someone type in chat or tell me?
Yes.
Okay.
Searching a graph. As the name implies, we'll use DFS to search a graph vertically before we proceed horizontally. When you think of depth first search, I want you to remember a stack, as this is the data structure that keeps track of vertices we'll visit. Let's perform DFS on the following graph. We want to know all the nodes that are discoverable from the root node A. Along the way, we'll keep track of two things. First, nodes we visited will be colored black. Nodes that are in the stack that are in line to be visited will be colored gray. Starting our algorithm, A is the first node we'll visit. We'll keep track of the stack in the top left corner. We pop A from the stack and mark it visited. We also add its adjacent nodes into the stack. I'm adding the rightmost node first because I think it's easier to follow visually if we go left to right. B is the next node popped from the stack. We mark it as visited. Notice G is the only node in the stack, but as we add B's adjacent nodes, G gets moved to the bottom. C is the next node we'll pop. C and D have no children, so nothing to add to the stack. We reach E and add its child F to the top of the stack. I'll let the rest of the algorithm finish without voiceover.
Okay. Then we're gonna jump to G. Okay. Did we jump to G because
I have a question here,
Yes.
please.
Yes.
Is he traversing the left subtree first before going to the right, or according to what? Yeah. What's the path he is following to traverse the tree in depth? Yes, in depth. Yes, depth algorithm.
And I don't know if we're free to start from anywhere.
You go
But
through the left.
we can ask.
You go through the left.
Yeah, but like, is there some rule that say you have to go through the left, or like
Someone shared it. Abdihadi shared it in the
I
chat.
didn't understand
Okay.
what rule he is.
He shared
following
that
towards the
Travis through left substream.
can you tag it?
Yes.
So this one. Oh, this picture. Okay.
Yes.
Let me open it. So, depth first search, traverse through left subtree first, then traverse through the right subtree.
He
Okay.
always go through the left. If there is a child, he go through the child first.
And
to check if there is two childs for the left and the right. He go always through the left one.
Okay. So it is related to the algorithm itself.
Yes.
I think the rule is based in stack and pop. If I'm wrong, need correction. I think deep first search use stack, so you keep them in stack, and I think the more you traverse, the more you keep adding more child. And the Brits first search traverse through one level of children node. We're gonna see this one. Let's keep focus on this one. The DFS. Someone said go back 1 minute.
Next node will pop. C and D have no children, so nothing to add to the stack.
Okay, so let me see. So in the beginning, the stack was empty. Then we add A because this is the
It's the first node we'll visit.
Right?
We'll keep track of the stack in the top left corner.
Then we move here, we remove.
We pop A from the stack.
So when you pop, it gets removed from the stack.
And mark it visited.
Okay, the stack is empty. But at the same time,
we also add its adjacent nodes into the stack.
Okay, so when we pop it, we also add their children because we have access for them from the root. We add them to the stack. Then now this stack have B and G. And we're gonna keep adding to the stack the more we go through the list.
I'm adding the rightmost node first because I think it's easier to follow visually if we go left to right. B is the next node popped from the stack. We mark it as visited. Notice G is the only node in the stack, but as we add B's adjacent nodes, G gets moved to the bottom. C is the next node we'll pop.
Okay. So we start popping when we reach the end of the level. So each level we start popping. So the first level was B, then we go this level. C. Pop it.
C and D have no children, so nothing to add to the stack. We reach E and add its child F to the top of the stack.
Yeah, I believe so. I believe each node we got to it, we push their both children, if they have, to the stack, so we can visit them later. Because we're gonna keep looping through the same stack, and each time we loop, we're gonna find a new node. Let's keep going. Okay,
I'll let the rest of the algorithm finish without voiceover.
Okay, I try to do voiceover. So here, F and G. So this is the last element we have in stack, right? Because we pop C and D, and because they don't have a node, we didn't add anything, right? So when we jump to E, we pop it, but it have a child, so we added F. Now what G does here, it's because like when we were in A, we had B and G. I'm not sure if you can see my mouse.
Yes.
Yeah, so like we had, when we were in A, we add B and G. So G, it was here for like from the beginning. Okay, we pop F. It doesn't have any children. Now we're gonna loop again to the stack. We have one element. We're gonna go to it. Then we're gonna pop it. But at the same time, we're gonna add its children. It have only one. We're gonna add ish. Now we're gonna pop it. We're gonna loop again, pop it, and add if it have children. Okay, so this is DFS, which use stack. Can you repeat, please?
Let's say the H, if it has left.
Finally,
side,
there is no.
He gonna pop it first. Then yes, the H one.
Yeah.
If it has like a G or X, he gonna pop it first, then pop I.
Yeah,
Because
like if it have two, if it have two children. If H have two children, you mean?
No, what he's trying to say is you pop the leftmost first before you start popping the right.
I see. Yeah. So
That's
you
what
always
it's
keep that left first. I think what we saw here. Traverse to the left. Okay, let's see.
That we pop the left as long as we have left children or left nodes, we pop it. Then we move to the right node. We never pop a right node until we finish the left ones.
Yes.
Yeah.
Exactly.
Yes.
Yeah. Exactly. Yeah, that's it. Nice one.
Because in this example, even if we have G, Monsef, can you back a little bit in this?
In the picture or the video?
No, the video.
Okay.
Go back when we have G and F.
G and F. Okay, believe.
Yes, with gray. No, go back. Yes, this page. Even if we have G and F, even if F is right and G is right, we go through F because if it was the child of a left node, that's why he pop it first. Even both G and F was right, but he go through F because it was the child of a left node. That's why, like it say, Shaza, always we finish the left one and then go to the right.
Yeah, if you notice here before, it had D, E, G. So he add E, he add A first to the stack, because when you're using stack, we pop from the top, right? So we name reaching B, right? And they found that it have 3 children. Which one I'm gonna add to stack first, C or D or E? I'm gonna add E because it is the last one that I will pop. Because when we pop from the top. So because I'm gonna visit C first, I need to add it the last one. Not sure if it's clear here. Okay, we jump to where we were. Believe here. Some more question, please feel free to open mic or write in chat. Let's keep going.
Finally, there is nothing left in the stack.
Okay.
So our algorithm is finished.
Okay.
Here's the code for depth first search.
Sorry, where is the stack?
Can you repeat? Can you repeat, Pascal?
Where is the stack? Where is the stack? Where is it?
A stack can be array. Like
No, I said where is it? I thought he's showing the stack. I can't see any stack on the screen. That's why I'm asking. Where's the stack?
Oh, this is just it's showing just like traversal. It's not like
Okay.
So this
I thought
like
it's
just
keeping it somewhere else. So
yeah,
pop it
yeah.
out or something.
But
Where is
for
it? Pop it out. I
example,
thought it's keeping it somewhere.
yeah, for example, if it was question, can you get all the value of this tree using DFS? We're gonna have an array that's gonna have E, B, C, D, A, F, G, H, E, and I, and it's gonna be the same technique of the that we saw.
Yeah, I get.
Let's see.
Nice.
Let's see what's gonna show here.
Here's the code for depth first.
There's some
search.
Okay, let's see. I saw some picture in the chat. Using Q. Okay, is this okay, this is BFS, right? I think this we're gonna see it in the next chapter. Now we're using
There's a link to a working Python
first, so it's gonna be stuck. Now let's see this code.
An example in the description. The code is very similar to breadth first search, except a stack is used instead of a queue. On the left is our graph represented as an adjacency list. Let's walk through the code on the right. We first add the root node to both the visited list and the stack. We loop while the stack is not empty, popping the top.
Okay, wait. Wait. He's using stack, right?
Okay, the code is very similar.
Because DQ you can use stack and you can use queue. This function of Python.
To breadth first search, except a stack is used instead of a queue. On the left is our graph represented as an adjacency list. Let's walk through the code on the right. We first add the root node to both the visited list and the stack. We loop while the stack is not empty, popping the top element from the stack.
Okay, as we saw.
We iterate through the adjacent nodes. Notice the reversed function that adds the rightmost node into the stack first. So we visit
for in reverse graph. What does reverse do? Does it reverse everything? Think reversed.
Reversed like an inverse.
Like it's flip them.
Order.
Okay.
Yes.
Python. Okay.
Visit it last. If the adjacent node has not yet been visited, we add it both to the visited list and the stack. Note that you can code this both iteratively and recursively. I've chosen the iterative approach here because I think it's easier to follow. Let's discuss time complexity, which is the same as breadth.
Okay, let's try to understand this code because I'm confused a bit.
Let's discuss time complexity.
What he was trying to do here. We have a graph. So we have keys A, B, C, D, and he does add. Okay, he append the value of each.
The graph is just like the tree. It's just like a tree. A has children. B.
Oh, okay.
C
So this is children here.
I think that. Yeah, okay. Maybe that's what it's trying to do.
Yeah, it's called an adjacency graph. It's exactly what Pascal has said.
Okay.
So it shows what nodes are connected to each other. Each of the nodes there at the keys.
Okay. Okay, make more sense now. Let's see time complexity.
Let's discuss time complexity, which is the same as breadth first search. If you think about our example, in the worst case, we're going to visit each node and explore every edge. Therefore, the time complexity of DFS is big O of the number of vertices plus the number of edges. Thank you for watching. Please.
Is number of what?
Time
Nodes plus number of
complexity
edges.
of DFS.
Okay, so this is DFS. Let's jump to BFS.
Today, I'm going to teach you breadth first search.
Let me pause the video.
Breadth first search, or BFS, is an algorithm for searching a graph. When you think of BFS, I want two things to come to mind. First, breadth means broad or wide. In other words, our algorithm will progress horizontally before we proceed vertically. Second, the important data structure for keeping track of vertices is a queue, specifically a first in, first out queue. BFS is best taught with an example, so let's use the following graph, which is a collection of vertices and edges. We want to know all the nodes that are discoverable from the root node A. Along the way, we'll keep track of two things. First, nodes we visited will be colored black. Nodes that are in the queue that are in line to be visited will be colored gray. Starting our algorithm, A is the first node we'll visit. We'll keep track of the queue in the top left corner. We pop A from the queue and mark it as visited.
Okay, this time is using array.
We also add its adjacent nodes into the queue. We also add its adjacent nodes into the queue. B is the next
Okay, so it is a queue. Okay.
node out of the queue. We mark it as visited and add its adjacent nodes into the queue. Same with C.
Okay, so when we pop from the start, right? Because it's a queue. Okay, let me go back again.
Will be colored gray. Starting our algorithm, A is the first node we'll visit. We'll keep track of the queue in the top left corner. We pop A from the queue and mark it as visited. We also add its adjacent nodes into the queue. B is the next node out of the queue.
Okay, so this time when we add them to the queue, we add the last one on the left side. If you notice, when we add here, we add the last one at the end. Okay.
We mark it as visited and add its adjacent nodes into the queue.
Mark it as visited. Okay, it have D, E, F. We add them, but C, it was still in the queue. So when we wait, how did he do that? Okay, because B, it was C, B, right? So B was here. When we pop it remove. Then C become the first one in the queue. Then we add. So we always wanna go from the left. So we're gonna add D first, E, F.
Same with C.
I'm gonna pop this one. It have G child.
Here, I'll pause our algorithm and illustrate what we mean by breadth. We visit nodes at the same level before we progress vertically.
Okay, I noticed that we didn't go for H like it was in DFS. In DFS, we focus on the left one until we finish the left one. Then we come back to the right side. But this one, we just finish the level. Then we stop. We jump to the other one.
D is the next item out of the queue. I'll let the rest of the algorithm finish without voiceover.
Okay, doesn't have any children. This one also doesn't have nothing. Puppets. This one. Okay, what's gonna happen in this one? We're gonna pop it. J is gonna be the first, then we're gonna add H, and then we should jump to G. Puppet. Okay, add H, now jump to G. Puppet, then add E, I. Okay, then pop H. Okay, I saw one of the picture you did post. Let me go back to it. Which one? This one? Yeah, so we did saw this one. Bridge first. Wait, yeah, bridge first search. Traverse through one level of children node. So level 1, 2. Then traverse through the level of grandchildren node. So the next one. Okay, there's other picture that we saw. Where is this one? Yeah, using Q to implement BFS. Okay, discover node, a node we add to our queue who location we know but we haven't actually visited yet. To start, the root node will be the only discover node. If we add it to the queue here, front of queue, end of queue. Okay, this is cool. I think everyone have idea about difference between BFS that use queue and DFS that use stack, and the main difference that the DFS we go through the left, we finish it, then we jump to the right. The BFS, no, we go through each level, we finish it, we go to the next level. This is a cool video that's explain the difference. I think we will need to understand this concept more. I will post the video in the chat, and let's try it.
I will show you what is the difference between DFS and BFS. So we will tell you by giving an example. So this is an example which I have already taken. So you must be knowing how to write DFS and BFS. So the DFS, one of the possible DFS ordering from this graph is 1, 2, 3, 4, 5. Oops, 1, 2, 3, 4, and 5. Okay. How this is done? Let us have a look. So in the DFS, first we will start with the source node. That is, suppose 1 is the source. Now as soon as we find a new node, we stop this node and start exploring the new node. So suppose the new node found is 2, then we stop the operation on 1 and start exploring 2. As soon as we find another new node from 2 which is adjacent to it, we stop operation on 2 and then start operation on 3. And since 3 doesn't have any other node adjacent to it, so it will return back to 2. And since 2 doesn't have any other path to cover, so it will return back to 1. And since 1 is now having 4 as its adjacent node which is not yet visited, so it will start exploring 4. Okay, and in this way 4 will start exploring 5, and since 5 doesn't have any other node to explore, so it will return to 4, and 4 doesn't have any other path to explore, so it will again return to 1. So what you can see is that in DFS there is backtracking. So you can see that DFS is having backtracking. Okay, as soon as a path hits a dead end, then it will return back. Okay, this is called backtracking. So if we try to write the BFS of this graph, so how it will be? You know that BFS covers everything level wise. So one of the BFS ordering can be 1, 2, 4, 3, and 5, because you know that in BFS, if we start from source, that is, suppose the source is 1, okay, then it will, in BFS there is a queue, okay, and every adjacent node to 1 is pushed on the queue. So suppose first we take 1. Okay, so 1 was in queue. This is the queue. Now every node which is adjacent to 1 is pushed onto the queue. So 2 and 4 will be pushed onto the queue. Okay, and after this 1 will be popped out, and then 2 will be explored, and every other node adjacent to 2 will be pushed, that is 3, and then 2 will be popped out, and in the similar way 4 will be explored, and every other node adjacent to 4 will be pushed, that is 5, and so on. This will go on until the queue becomes empty. Okay, so this is how BFS works. So you can see that in BFS there is no backtracking. So this is one of the major difference between DFS and BFS. That is, in DFS we have backtracking, in BFS we don't have backtracking, because BFS uses queue and DFS has backtracking because DFS uses stack. So this is another point of difference, that DFS uses stack and BFS uses queue. This queue is used by BFS and stack is used by DFS. So one more point which you can make out is that BFS follows FIFO ordering, that is first in first out, because it is using a queue, and since DFS is using a stack, it will always follow LIFO, that is last in first out, because the last to be entered will be the top of the stack and then it will be popped out. So we saw three major differences. So now we will see the major difference between DFS and BFS. So you see that in DFS every node is actually storing only one child pointer, because as soon as we are at a node, suppose we are at 1 and we find a child which is unvisited, that is, suppose it is 2, then we leave 1 and start exploring 2. So 1 should only remember about 2, so it stores only one child pointer. But in case of BFS, it will store every child pointer of a node. So suppose 1 is there, and then it will store 2 and 4, so it is storing two child pointers here. So for ternary trees, suppose for Chiari trees, BFS will remember k childs, okay, k child pointers, but in DFS it will only remember one child pointer. Okay, so you can see that the space requirement for DFS will be very less as compared to BFS. So this is one of the major differences between DFS and BFS. I hope you have understood all the 4 points, and if you have any question.
Thank you so much. Okay, now I think we all have idea about DFS, BFS. Let's see how we can solve these problems, starting by, let me share full screen. Okay, I think we can keep it this right, so you can also see the chat. Share, change screen. Okay, so where we were, the first problem, this one. Okay, let's read it. Scan it around. See how we're gonna solve it. Okay, ignore this. 3. So let's read it first. What is this about? Maximum depth of binary tree. Now, a binary tree maximum depth is the number of nodes along the longest path from the root node down to the furthest leaf. As we know, leaf here is 15 and 7, and the depth is like 3, right? Because 1, level 2, level 3. So it have depth of 3. A binary tree maximum depth is the number of node. I think 3 because this is 1, right? I could be wrong. It's me. Let me go back to Shaza block first. What is depth? Depth. So depth of a node is a binary. Okay, so you may be right. Yeah. So this is depth 0, depth 1, depth 2. Okay, I think I had it wrong. So 0, 1, 2. Is this correct? Okay, let's read that again. Maybe I misunderstand. Binary tree maximum depth is the number of node. Oh, okay. So I'm mixing level with
correct.
depth.
3.
Yeah,
yes,
but
3.
I'm mixing the way I said it is wrong. It's not level. So it's the number of node along the longest path. So the longest path is this one, 327. So the number of node in this path is the depth. So in here, so the root node has depth 0, right? Its children have depth of 1. So here, these children have 2 depth 2. This one have 1. So the longest depth here is 3. I believe is 2 plus 1. Okay. So this, because a binary tree maximum depth is the number of node along the longest path. Okay, so it is 3, right? Everyone think it's correct? Wait, let's see the example. Yeah, the output 3. So it is 3. Because depth of this level is 2, and depth of this node is 1, and depth of this one is 0. So 2, 1, 0. 2, 1, total is 3.
This output, not the image. Output for the example, not the image.
Yeah, but like it have the same numbers. 3, 9, 20. 3, 9, 20. 15, 17, you see? 3, 9, 20. So this is left child. This is the 20 is the right child. Now 9 doesn't have any child, I think that's why it's null. And it doesn't have a right child, that's why it's 9. Null.
Yeah.
And then 20 have 15, 7, 7.
I think على ما أتذكر the depths the lion 7 have 1 depth.
No, and this have 2 depth of 2, 7.
Yes, the line 1 above and 1, 2, 3. The line this depth على ما أتذكر. I don't.
Okay, let's see this picture. I can see that spot. I found something different in the internet. Okay. So 3A, 3B, size 5, depth 4. So
the line between A and B, the line between B and C, the line between C and D, the line between D and E. The depth is the line. I think على ما أتذكر.
Okay, I see. So it's
you're counting the edges.
You want the number of nodes. You want how many nodes we are going to pass along to reach the longest in our longest path. So
exactly. That's it.
Or maybe how many generations?
So this is have depth of 2?
Yeah, generation, yeah.
Why did you say 3 here?
But the number of nodes we are going to pass is 3 and 20 and 7.
Okay. Okay.
It's number of nodes, exactly.
What is maximum depth of a tree? How to calculate that? So I think you guys are right. It's like the counting the edges. That is the depth of the tree, but maybe maximum depth is different. The maximum tree is measure how deep the tree is, and it's defined as the length of the longest path from the root node to the leaf in the context of various tree structure such as decision tree, binary tree, and depth is important factor. Okay, which is the maximum depth we gonna count the edge or the node in the longest path. I'm confused because when we wanna calculate
Monsef, what is an empty?
Wait, give me a second. Let me finish this. I'm confused because when we wanna calculate the depth of tree, we count the edge. Yes, Omar, go ahead.
So if we have like just an root node in our tree, is it we have like this tree have depth of 1 or 0 depth?
Can you repeat that?
So if we have like just the root, we don't
depth
have
is 0.
Yeah, depth gonna be 0.
Yeah.
Because we are right. They give us the root, so there is no depth. There is no deep to go through. So it's 0. So we don't count. We don't take the root node in count. Okay, that's
yes,
what
we actually do. It's just the count that starts from 0. But the maximum depth. The root is counted, and second one,
that's
third
why.
one, and fourth one.
It's not line. It's not about line.
Okay, why is the answer 3? Why they get 3 as the answer?
Okay, here's it. Like Moji said, this one we're gonna count it. So what is the depth of this? So 1, 2, 3, 4, 5. So this is the max depth.
Exactly.
This is the max. So there's a difference between max depth and the depth of the tree. And let me verify here.
The max depth is the count of nodes each node.
Okay. So the convention for calculating the depth of tree may vary depending on the context. Node count convention, edge count convention. In some contexts, when people refer to depth of tree, they are counting the node along the longest path from the root to a leaf. The depth will be the number of nodes in that path, not counting the edge. In this convention, the depth is the number of decision node or level. Edge count convention. So there is 2 different conventions. In other contexts, when people talk about depth of tree, they might be counting the edge along the longest path from the root to a leaf. The depth will be the number of edge traversed in that path. In this convention, the depth is the number of edge or branch. So it's like there is 2 ways to know the depth of tree. That's why we're like here confused, right? Now I guess we are forced to follow this convention of counting the nodes. There's another picture.
I think so.
Okay, this one have
the example that which is provided by Alex is like counting the age.
The age, yeah.
Yeah.
Okay, so this depth 3, depth 2, depth 1, depth 0. what is the maximum depth is 3 plus 2 plus 1 plus 0, which is
it's not 3 plus 2 plus 1 plus 0. No. So we can start like counting from the root, but we don't take the root in count, okay? Like this 1, 2, 3 edges.
So like if we're gonna if we're gonna read like say the max depth with edge, we're gonna say 1, 2, 3. So this max depth is 3.
Exactly.
But if we're gonna read it from the node, we're gonna say 4.
Yeah.
If you can see the link condition.
Okay, let me see. Finding the maximum depth of a tree. The maximum depth of a binary tree. Let me zoom. Oops. Wait, there is no way to close this. The maximum depth of a binary tree could easily be found using simple recursive algorithm. The maximum depth would be plus 1 plus maximum of depth of root left subtree or depth of root. Oh, so this is the plus that we are like talking about. So 1 plus maximum of depth of root left or depth of root right. So they add 1 here to count also the node, the root node. Because this, if we count just the edge, it's going to be 1, 2, 3, 4. So this tree have a depth of 4. But we're going to return 5 because we're going to add 1 here. We're going to count also the node, the root node. Okay. I guess we understand why it is 3. So how we gonna do this? Are we gonna do it with DFS or BFS? I think DFS is better, like stack or like a recursive way. So let's go to Excalibur and brainstorm together and see how we're gonna do this. Why I'm so zooming? So, let's see the question. Given the root of binary tree, okay, we have root here. A binary tree maximum depth is the number of nodes along the longest path from the root node down to the first leaf. So we have the root. If we're gonna use like DFS, which is like stack, right? What we saw is we go to this, we add it to the stack tree. Oh my god, what the heck? Okay, we add it to the stack tree, right? Then we take their node, we add them. Wait, is this stack or queue?
DFS. Yes, 9.
It is, right? No. Okay, so we add.
This is a queue.
This is queue, right? Okay. How are we gonna do it with stack?
If it is a stack, the 20 goes in first before the 9.
The what? Oh, the 9 first?
The 9.
Okay, yeah. Okay.
We start from the left and we go to the right.
Okay. So this is our stack. Let's say we go to the root. Yeah, I remember now. Okay, so stack, we go to the left one.
Yes,
we add it. But in recursive, we start from, like, we're gonna do it in recursive. What do you think? We do it in recursive. So we go here, then we check the left side, the left, and the left we're gonna see we're gonna return it to the root. Okay, I'm trying to think about like a recursive way.
Let's define the base case first. What's the base case here?
If we reach here, it should stop. So maybe node equal null. Maybe if root. I think root we have here. Root. So we can do like if root. If root equal none is none. Then we're gonna return how many children? It's gonna return 0.
Access next, or if you don't use linked list, you don't. Yes.
Okay, think with me. So we are using DFS, right? And recursive. So we need a way to go here, and this should return to this. How many? What the number? It should return 2. 2? No, it have 0, 0. So it's gonna return 1, right? Because it doesn't have anything. So 1, this one, it's gonna have 1 of this, and it's gonna return 2 to this. So it's gonna get 1, and it's gonna add 1 to it, which is itself, and then it's gonna return to this 3. No, sorry, 2. And this one gonna return 2 plus 1, which is 3. Okay, wait. So this gonna return 1, and this gonna add to that 1. It's gonna add to it plus 1, and then it's gonna return to this, and this gonna add to this 2, 1. So this way, when we're gonna start recursion here, it's gonna go pum pum, and then it's gonna return 1 here, 1 here, and this one gonna return. Okay, it doesn't have nothing here, so it's gonna return 1 to here. But we need to compare, so because this one gonna return 1, and this one gonna return 2. So we need to compare the maximum one that we're gonna return. Oh my god, the most hard thing is to explain recursion. Any idea? Is my idea clear first, or maybe I put you guys in dark? So let me try to explain what I'm trying to do, or we can change this idea and see if someone have like more easy idea. So my idea is like we do it in recursion, and what we're looking for is like to smear chat. We are looking to count the nodes, right? Oh my god. So my idea is like to traverse to the end and return 1, because we have 1 node here, right? And then this gonna come here, and so each node we launch like 2 recursion, 1 on the left side, 1 on the right side. So it's gonna be counting node. So it's gonna be left plus right and left plus right? No, not plus. It's gonna be the maximum of them, like
the
biggest one. So max plus 1. Because if I am in 20, right, and I launch like 2 recursive function, one it's gonna go take care of the left nodes, one is gonna take care of the right nodes. When this recursion finish here, I need to return a value to tree, right? So this value that I'm gonna return, it should be the longest path. Because if this have more nodes, I need to return this value, the longest path. So I need at some point to compare the value that I'm getting here with this one. And then I'm gonna add plus 1 because this one itself, it's a node. Right? So this one may return 7, may return like 7, and 15 may return like 5. That means there's 7 node here and there's like 5 node here. I'm gonna compare them. I compare, it is 7, okay, and plus the node 20 is gonna be 8. Then I'm gonna return 8 to this. It's like saying, hey, node 3 in this path, the longest path is 8. So max left plus. Someone said something but I didn't hear. Okay, let's copy another picture because I destroyed that one. Okay, we said we're gonna do if root is none, return 0. This is the base. And now we're gonna do what we call max left right plus 1. We're gonna return it, right? Return. Okay, so this gonna be recursion. So left is gonna be left equal, what's our function called? It's called max depth, and you give it a root. So it's gonna be max depth. Okay, we have self dot left and that's right. So it's gonna be max depth. We're gonna give it root dot left, I believe, and the right is gonna be what? It's gonna be the same. Max right. So when we're gonna do like this max depth here, it's gonna launch a recursion. So wait, I think something is wrong. Is it if return 0, then left, then max left max. Okay, let's see. Maybe I'm just okay. So I am in the root. Okay, root it's not equal none, so it's gonna go here, right? It's go to the left. It's gonna call a recursion function, max depth. It's gonna give it this node. So here there's gonna be another function that's gonna keep looping through this, or like it's gonna execute through this node. This gonna be the root node for her. Now in same time it's gonna go also on the right and gonna launch max depth. Or not in same time, it's gonna wait because it's gonna wait here until this return, then it's gonna go here. So what's the value this gonna return, or what it's supposed to return? It's supposed to return 1 because there's only one node in this path, right? So we need this should return 1. So left value is gonna be 1. Now when this become 1, the right gonna pass. But let's see, is this formula right here is gonna give us 1? Yeah, because the left, because when it's gonna come here, the left's gonna be none, right? Because it doesn't have left, doesn't have right, none, so the value is gonna be 0, because the max of 0 is 0 plus 1 is gonna be 1. If someone struggling with recursion, it's gonna be hard to understand this, but just like check maybe the PLD we did in recursion. It may help you understand more. Now let's see if this right here it's gonna give us the value. But before we do that, let's see what it's supposed to return. It's supposed to return 1 plus 1, so 2. So it's supposed to return the value 2. So it's gonna go here. It's gonna launch this one. It launched it. Okay, this function did go check here and here. It go to root. It's not none. It's gonna launch another max dip function here and here, and this one gonna launch another one. This gonna return 0 0 0. Here it's gonna have 0 plus 1. Here again 0 plus 1, which gonna return it to this, which is 1. Max 1 and max 1 is 1, plus 1 is 2, and this gonna return 2. So this is correct, but let's see if it's gonna work in code. If someone have question, please go ahead. Do I have to change something? I don't think so. Maybe. Let's see. What is not defined? Oh, self, I believe. Self. Okay. Okay, it works. Now how we can
try to submit it if sometimes it works, sometimes there's edge cases.
Okay. Okay, it's not bad. Now let's say we did this and interviewer was like, hello, you finish it very quick, now give me the iterative way, and you will be like, I'm sorry, I don't know how to do it. Now let's try to do it with iterative way, which gonna be what is that, a BFS or DFS? So this is DFS, right?
Yes.
And iterative way, is it
I think we can use either search method,
which is BFS, the Q
or BFS.
Yeah.
Okay.
BFS.
The Q might even be much better.
Okay, let's do it with the Q.
Yeah. I was also thinking the Q is.
Wait, can you repeat, please? Someone is trying to talk, but your volume is very low. Can you repeat? Hello?
No, I was just saying I was thinking the Q is easier, but the solution you did using DFS, the stack also it looked a bit short and interesting.
Okay, we use do we use what is called BFS?
Yeah, BFS using Q.
That's right. Okay, so how it's gonna be with BFS? Let's see. So BFS, if I don't remember, someone help me, please, or let me see this picture.
BFS, maybe we go line by line.
Okay, line by line.
First, so left and we go
left, right.
right.
Okay, so we're gonna go to the left, then Okay, we added to the queue,
20.
right? So we're gonna add 3 to the queue. I mean, no, because it is the root. I don't think we add the root.
You add it.
So yeah, we add 3 to the queue. Then we add her children. But which one we gonna add first? The 9, because it is the
9,
the one we're gonna pop.
9,
then
20.
20.
15.
And then we're gonna jump to 15. 7. But each time we add them, so when we add this, we pop this one. When we okay.
So
when we pop this,
you pop the 2 next. Or
so
you pop one of them. Add.
Okay, so it is add this, then the new queue gonna be pop this. Okay, it's gone, but we did add 9, 20.
Yeah.
The new queue gonna be pop this 9 pop. It's gonna be only 20. Then pop 20. It's gonna be 15. 7. Then 7. And then nothing. Okay, can we know how we gonna know the depth from this? Maybe 1, 2, 3. Okay, so where is the loop stop? So this is the first loop. This is the second loop. And this is the third loop. So it is 3. Because here when we pop a left and the right. So left and the right. So it is same loop. So first,
when you
yes, let's go ahead.
When you pop the left of the second level, when you pop the left of the second level, you add the left of the next level.
So when we pop the left of the first level,
yes,
we add the right level.
No, you add after you put the root. After you put the root, you pop it. Then you then add the left, then the right. In the next, that's in the next queue after popping the root.
Okay, so the loop is gonna be about if the queue is empty. So as long as the queue is not empty, I'm gonna keep looping. So the first loop, before we enter the loop, we add the root to the queue. Then we enter the loop. Let's say this is our loop, right? It's gonna keep looping like this. Now the queue have the value 3. It have only 3. Then we can do like so. I add 3. Now I loop. I'm in the same loop. I'm gonna pop this. Pop this node.
Yes.
And then so let's write this in then. So loop pop node. Then we're gonna add the left and the right child, which gonna be 9, and 20. So this is the same loop, right? Loop number 1.
Yes.
So we're gonna add
count each time we have two values or more in the stack.
Maybe a counter. It's gonna work well.
Each time we have 2 values or more.
So
because that's how we can know.
We're gonna say add left and the right to queue. Okay, so we pop the node that it was there, and then add left and right to the queue. Now we're gonna loop again.
And then you pop the left, then add the left of the next level.
Sorry, why are we popping? Why are we popping it? Because if we are popping it, how do we get the length, the longest length? The longest, count the nodes that has the longest path.
Because each loop, because we are looping through the queue. So to the loop to stop, there should not be any. At some point when we're gonna reach here, the queue should be empty. So each time we move from level to level, we pop the nodes. So
all right, just go ahead.
Okay, I'm still thinking. We add this left and right. Now maybe we have, like you said, counter. We increment a counter, right? So C.
Yeah.
So C. Let's say C is this one, right?
He checks when we have two or more values in the stack.
Okay. So no, I think just the loop itself is enough because notice that we loop each time we move from level to level.
Okay.
So we can count that.
Yes.
So first it was 3, right? Then we pop this node, the queue become empty, but in same time we add left and right to the queue, which is this one. Now when we add them, another loop starts right here, loop number 2. Now the queue, how many nodes we have in the queue? 2, right? So queue we have 20 and we have 9. Then we're gonna add. Okay, so this one is gonna be confusing like this. Maybe if we did like how we can do this so it doesn't be confused. Okay, maybe we do it separately. Add left to queue and add right to queue. So we loop a second loop. Now we are okay. We're gonna what? This loop we're gonna focus on 2, right? Because when we pop, only this one that's gonna be treated. Because each loop we're focusing in this one, the first one in the queue.
Yes.
Because when we I think I'm writing a very bad. So we have node, pop, or like pop left. I think pop left.
No, pop should work.
Say Q. I think last time we did it with pop that it didn't work because pop is because we are using DQ and to pop in the queue it should pop left.
Yep, we learned that the hard way.
Yeah, so left, like what I'm saying. No, it's like it's been a queue. Append. I'm gonna append the left one, right? So this is the queue. Append 9. So this is left. How can access the left? We have node here. We did pop this tree node. We have it here. So we do node. That's left. Because each node have left and right, I can access to them. So if I pop this with left to node, then I can add q append node left, and I can do like q append node right.
I think the left the next index, the right the next index, because in Python it will be array, not linked list. I think. The left,
you mean this one?
Yes. Then this node index in array.
No, this is not array. So it is a class. It have attribute left and there's another one attribute right.
Yeah.
So we're looping here. We're gonna do like what? While the q, and the q is equal dq, I think. Python dq. Yes, dq. In dq we can put root inside. So dq, then so at the first we have in q only tree, the root tree, right? Then while the queue is not empty, we're gonna go to this queue pop left, which is gonna give us tree, and we're gonna go to the queue is gonna be empty. Then we're gonna add to the queue the node left and node right of this tree, which is 9 and 20. Now we did loop again, right? Okay, so this is the first loop, I guess. When we loop, we add them. So this is here is wrong. So this is one. The first loop we have in Q 29. So this is before we enter the loop. Counter +1. Yeah, we can do counter. Counter +1. Now this counter gonna keep looping, but let's see if it's working or not. Maybe we're missing something. Let me repeat this. So first loop, it's gonna in Q we already put Q here. We put it in Q, so Q have 3. Now the program gonna start here, the loop. In the loop Q, we're gonna pop, and then we're gonna append 2. So the Q is gonna be 20 and 9. Right? Now we're gonna counter gonna do +1. Let's do it like here. Counter gonna be 1. C0. Now we're gonna go to the next loop. Q gonna be what? We're gonna pop 9. 9 is gonna be pop. It doesn't have any node. So maybe we need to add check here because it have null here. So let me just put check here. So like if node left exists, then I'm gonna append it. If it doesn't exist, I'm not gonna append it. So this is check. Just to remember when writing code. And then we're gonna do what's counter +1. So 9. Right, 9. Okay, Q. What the value of Q? We did pop 9, so the value is gonna be 20. And C, we increase it. It's gonna be 2. Now another loop. Now another loop. This time the queue have only, let me write another queue. It's gonna be 20.
But if there is nodes after 9, you will pop 90 before the left node after 9.
I'm gonna here. Yeah, I'm gonna pop 9.
Yes,
in the next loop I'm gonna pop 20.
If there is node after 9, you will push this node and
yeah, they're gonna be here, right?
Yeah.
Yeah.
You will pop 20 before the node after.
Yeah, because this is what BFS, so we go level by level.
Don't not lower and you're going to the all nodes, not the أصغر أكبر the less.
Oh, you mean we start from the bottom, right? That's what you mean? Because I think we start from the top and then we go here, then we go here. So
I want to understand what do you do.
Like we go from 3, right? We did start here, right?
Yes.
And then we move to this level. Then we start from left side. 9. When we finish this, when we finish it, we move to the right side.
Even if the 9 has a child, we go through.
Even if it have like a child here,
you will
like
go,
this, we will go to 20.
To 20, no, yeah.
But this child, we're gonna add them here. We're gonna see how it's gonna work here.
You best all nodes, not the last node before the bigger node. يعني انت بتمشي على النود كلها، مش الأصغر الأول وبعد كده الأكبر.
Like the value?
Yes.
No,
yes.
we don't check the value. We always start from the left.
On the left.
Even if it was here 20 and the here 9, we're gonna start from 20 the left side.
Yes, okay. That's right.
So this loop, the first loop, second loop, this is third loop. We have only 20 in the queue because we finished with 9. Now we are here. Now we pop it here. We pop it, which means it's get deleted. The queue is empty, but in same time we append 15 and 17. So the queue here. We can design this. Yeah, I will just add them here. So 15 and 7, not 17. Now the queue have 15. Yes, Mahmoud. And C should be 3.
This would be right.
Yeah, I think it might work. Let's see. Let's see what's gonna happen here. Now we're gonna move another loop. And this is loop number 4. And we're gonna go to queue 15. 15. I mean, we're gonna go to 15 and we're gonna pop this one. Let me make this better. Okay, so we are in 15. The queue have. What's the queue have here? It's have 15. It's gonna be, we pop 20, so it's gonna be only 15. 7. And then the Q gonna be, we're gonna pop this. It's gonna be only 7. So the Q gonna have only 7. And we're gonna increment C. So notice here it's 4. So maybe we should start with 0, not by 1. Maybe we should, but let's say it's at the end of the... Yeah,
what
maybe
about
here...
if you have two pop left?
I think I did mistake
one above,
here.
one below.
Hmm? Two. I increment.
Can you hear me?
Yes, can you repeat what you said?
I said, what about if you have two pop left?
Two
above
pop left.
and down after the right, after you put the right, the node that's right, you have another pop left again just before it.
Like you mean 15 and we have children with the 8 or something like that?
Exactly. Like after left, right, then you pop left, then you count, you go back, like that.
But it's still the same is because we go line by line and we count each time the loop each run we count, so it's the same case even if there is
we are looking at the termination point where the queue is empty. I think that's the termination point, right? Where the loop has to
yes.
Okay,
yeah,
I think this will work, but here we should do counter
-1,
counter 0,
or we do -1
because let's see, we pop left, then we append this and this to the queue, and 3. We're gonna append this left and right, 9 and 20. Now in this code we pop left, right? Now we have 9 and 20, right? Now counter is 1. Now I'm gonna loop again. I'm gonna pop this 9, move 20 here, and add 15 and 17. 15 and 7. No, I keep saying 17. Okay. Now I did pop 9, 3, 9. I did move to 20. I did pop it, and I add 15, 17. This is in the same loop.
So it will
and
not
then
increase.
It become like 2.
Yes.
Now here's where's the problem.
15.
So something is missing. When you're gonna go to 15, it's gonna what? Pop it, add nothing to the queue, add nothing, and it's gonna increment the counter. It's gonna become 3. And then, so something is missing, this is not working. Then this 7 again.
Pop 7 and finish.
Pop 7, and then nothing gonna be appended. It's gonna be 4.
There's thing I don't understand that we in this accepted problem we return the size of node, not depth. Can you go to the requirements, the depth or size?
No, we should return 3. So 1, 2, 3.
The code accepted. I think if you print this, will return 5. 1, 2, 3, 4, 5.
No.
Can you print this Before you change code.
Okay, yeah, but now we want to see like why this return 4 and like how to make this work.
We have to make
maybe
a condition. Check.
Maybe condition.
Sorry, if you sorry, Musif, sorry.
Yes.
If you make sure that you finish one level before going to another level, you will get the correct stuff. Like complete one level first before you go to the next. The next level should be another loop. Do you understand?
Oh, okay.
That's what I'm
So
saying.
I see what you mean. Yeah, because if you notice, I increment here and I increment here, but that's wrong. We append them both in same loop, so it is 3, not 4. This is my mistake when I was.
So it will out in the.
Yeah.
The time when we have 15 and 7 in the stuff.
Okay. So
let's try it and figure out.
Okay, so my mistake here, I think it's not while Q, but we should because if we did while Q, it's gonna every time loop on each element in the queue. We don't want that. We want it to loop on each level. How we can make it? So maybe we add another loop inside.
Right or left R2.
But did you get the problem?
I said why we can do while right or left are true.
While right and left are true.
Yes, or. Not only and, or, yes.
But I didn't understand how we can... What that mean, while right and left and true.
What he's saying, if that node has children.
Yes.
If this node, so while left and right are true.
I
don't get it.
I guess we should use or because we use and. Maybe we have many childs without left or right. Only left or only right.
But that's not the problem. I think the problem is like when we let's see, the problem is clear in the last loop here.
Yes.
So here we should, before we loop, this should be empty. So every time, not empty, yeah, because there's nothing.
Exactly.
But like here,
it has to empty for a new entry.
So we have to put a condition in the like condition. Wait.
So what I believe or what I can get from what he's saying is so for example, if we go to the root node, it has both left and right. Yeah, so when we go to the left, it doesn't have left and right, so it will not look for that one.
So if it's to go to 9, it doesn't have left and right.
It won't go through this loop since it doesn't have either left or right node. So in the case of at the end of the day, we will only use the longest node or the longest path.
Musif, you can start with one if there is node and if
okay, wait, let's go one by one. Let's try to understand this one that he said. So because if we speak all in the same time, how we can understand. So this if he said like do a check here, if there's left and right exist, then you can go, or one of them exists,
or one of them exists. If one of them exists, then it will do the loop.
Okay, so that's gonna stop it from
to stop
here.
there.
Okay, this could work, but how can do that? While
So we just use left. Would that be roots dot left, or then that means we change the whole code then?
Yeah, I think if we did that, this algorithm is not gonna work because we are looping. Okay, I think I detect what's wrong. Mahmoud, what you were gonna say?
Okay, I think if you can start counter with one, okay, and while q dot left and or q dot right plus plus otherwise don't increment this. I understand.
No, I did not. Can you repeat, please?
If there is node, if node not node.
Okay.
Okay. Counter equal 1. Okay.
If node is none.
Not
none.
If there is node. Equal one. Wait. If there is one node, we should return 0, right?
Yes.
Yes. Sorry, this in the while loop. In the while loop, if there is if node dot left and or node dot right plus plus else don't increment counter. لو في if there is node in left and right or right, increment the counter. Else don't.
Okay, I still feel, I see what you mean, but I still feel we are fixing a bug. So why not look for the bug and remove it, not just fix it? Because this algorithm itself, without fixing a bug, it should work. Because notice you move from level to level.
Monsef.
Yes, man.
If I may say, like the first algorithm we used, the issue with it is that if we loop, we will be looping 4 times. So it's gonna be the counter is gonna be incremented by 4. Is that right? That's right.
Yeah, so the bug we have is when we are in this level, the loop should be only 1, but for some reason we loop here and then we go loop here and then we go loop here and then we go loop here.
Yeah.
So we need another like for loop here or while loop.
So like that's actually correct. So if we loop here, we need to do a while loop inside the while, I think.
Yeah.
So we can loop. So we can add left and right.
Yeah. Let me try.
Okay, sorry.
Can you practice? Sorry, Muslim, can you hear me?
Yeah. Yes.
Can you practice the algorithm again, like the pseudocode, the way it was practiced?
Okay.
So when you put the node,
I will appreciate this.
Okay, let's try to do it again. Let's do it together. So,
can you try this condition instead loop?
Nested loop.
Instead, this condition I was told you if there is left and or right increment, else don't increment. I think this will.
I think it will work, but I think it will be like we're fixing a bug, like because it's like the main algorithm BFC it will allow us to count the levels. So what we did is we write wrong algorithm that have a bug, and we are looking for solution to fix the bug instead of fixing the algorithm itself. Did you understand me, Mahmoud?
A little.
If
Okay.
I might interrupt.
Yes. Yes,
How
go ahead.
about we keep like the counter related to each like part of the tree? So when we get to 9, it is still connected to the depth of 9. And then while we keep going, we keep incrementing its own counter.
So for example,
when
here
we get to 20, we get to 20, it has a counter of 1. We get to 15, you add to that one. You don't add whenever you want. So maybe like an array of some sort that keeps both the node and its own counter.
It is the array. It's like the queue is like array.
No, but like an array inside of an array. So the root
like
that has its own counter. So root
and like
a
depth
for
here.
example, 1.
Like we add depth, for example, for each. Okay, I see. Okay, this may work.
Yeah, it's gonna work. It's gonna work. Yeah. The index like index to the depths.
Okay.
Yeah.
Okay, this is a good idea. It may work. I think it will work if we keep like each movement we increment a counter.
How we
that's
can do it.
But what you think if we fix this algorithm fix first?
Yeah.
Or like let's explain this algorithm. I'm sorry, Mahmoud and Sabah. I hope you don't feel like any your idea. But like I want to fix this algorithm because it's like a simple base. It's like we watching the video, but we couldn't implement it well. Now, let me explain where is the bug or where's the problem. So, in the queue, we have queue, or like let's say counter, right? So, this is level 1, this is level 2, this is level 3. We go to 3, right? While 3. We push it here. We push it here. Now we are in level 1, right?
Okay.
1, 2, 3. 1. And this is level. Is it level? Do we call level 0 or level? I think level.
Maybe 0.
1, 2, 3.
Okay.
Is it level 0 or level 1, 2? I think it's up to us. Let's figure out later.
It's up to you guys. Yeah, it's level 1 actually. Level 1.
Okay. So we add 3. Okay, 3 added here. We did not queue pop left. Because when we start in the queue, we start with this. Let me make it bigger. We start with this. Now we did pop left. Now here's where this problem. Here. In this part here, when we enter the while queue, there is something missing. We need to find out why.
So I'm thinking you might need a nested loop.
I think so.
That's what I think. Yes. And within that nested loop, you're still going to be popping left as well within the nested loop until that loop maybe empty. Then you start again.
Shouldn't we have to avoid it? To avoid the nested loop?
Yeah.
I'm not sure.
But I think nested loop is better than recursion in our case. Yeah.
But let's try to figure out using.
Okay. Let's try to see what is the problem. Then we can maybe do a better solution. Maybe the solution with the depth, like adding another parameter here, is gonna be better.
But
because we don't want to while loop or like to for loop. Yes.
The problem here is the counter. Each time add another marker,
and it should add only when level change, not the node change.
So if we
okay, let me finish like a visualization for like this code. So we add like 3, right? Now we go to pop. What I'm gonna show is how it should work. We're gonna pop 3 and we're gonna add 9, and we're gonna add 9 and 20. Now here the level is 1, right? And when it's gonna finish, the counter gonna be +1. Counter gonna be 1, right? Okay. Now we are still in the same level, right? I should not loop again, because if I loop, it's gonna add. So maybe I'm gonna do for loop on the queue. So maybe for let's say range length of the queue. So this way I only add the counter after I finish the loop, the length of the queue, right? Because if it was the last element, then there's nothing in the queue. Is it?
But you are adding to the queue as you are removing from it.
So this gonna keep looping?
Yeah.
So it will remove it, then add again, add left, add right again. So I think the add left, add right should be outside the phone loop. Does that make sense? Yeah.
I don't think so.
What you are trying to do is clean the queue so that you can put in a new level's values.
And one thing is like, okay, go ahead.
Can you repeat?
So what I'm saying is, so in the for loop, what you are doing is, so when you get to the for loop, it checks what the length of the queue is, then it pops what is in the queue, and after popping, it will add the left and right value that you have of the left and right value of the nodes you have popped to the queue. So if you are doing it in the same for loop, it will just add it again and then increase the counter, then start again and pop it again and add it again.
For infinity.
But like, I don't think this length.
Yeah. You don't think this the length ran twice?
Yeah. So when we append it, it have the value of old length.
Yeah. The current length.
Yeah. So that's what we're missing.
No, I think the old.
So because we did like length of queue, right? Which is 2. Like here.
What about
yes.
Variable.
Okay, wait. So, but wait, this is 4, right? Let's say 4. When you do 4 length queue, it's like you're saying, hey, run twice. So even inside the loop, I add something, like I add element, it's still gonna run twice, even if the queue has 3, because 3, it gets added after inside the loop.
So we have to give it the current node.
Okay, let me explain. So we did do while queue, right? What that mean? That mean this code what here, I'm gonna keep running until this queue is full empty. Okay, that's good. That's nice. Now inside this while queue, we are doing the for loop. What this saying is saying, hey, you're gonna run this on the length of the queue, which is the number of the what node we have in level. For example, we have 9, 20. You can see it here. So it's gonna go to this, it's gonna do something, it's gonna again loop again and go to 20 and gonna do something, and then when it's gonna finish we're gonna do counter 1. So notice our problem that we had before is solved, because this time and someone was saying like, okay, but we append to the queue, so this range gonna change, but it is not dynamic, like the value is already got from the start.
Yeah, and this is gonna fix the different sub trees problem.
Yeah, but I don't think this is a good solution. It's very
why
not it doesn't have, I think, good performance because we are using 2-4 or like 2
no, it's better. It's better than the recursion. So in recursion we use like we did callback. We took callback inside of a function. It's
but Omar, we have to avoid the recursion and the nested loop.
We have to avoid it. Avoid both. Why?
Yes, both. Just to make it more.
No, what I mean is the function with the recursion is it has like a giant time complexity. Yeah.
Yes.
Omar, I think what I remember, if you build the stack, you should use recursion instead. You build the stack because recursion, the kernel, the device build the stack better than you. If you build recursion, use function recursion instead that. I understand. In Arabic and you translate. لو انت بتبني ستاك، احنا حاليا بنبني ستاك. لو انت بتبني ستاك اللي انا افتكره انك افضل تستخدم الريكيرجن بيبني ستاك، فالريكيرجن هيبنيه افضل منك او افضل مننا يعني. ده انا ما اتذكر. لو انت احنا حاليا بنبني ستاك with the queue.
نبني كيو.
يس، احنا حاليا بنبني ستاك، فالافضل انك تشتغلها بريكيرجن، هو يبني الستاك، هو مش احنا اللي نبنيه.
Okay. Yeah. So
can you translate for
okay. So you see, like we using right now we're using built-in stack.
Contour, I think.
Yeah, we built-in stack, so it's better to use recursion than build it for ourselves. Okay, I think so, but I don't know, because if we take like for example in the last recursion example, maybe the last one, yeah. This example, the current example, we use like recursion. We do a twice callback. We do callback function twice, so it gives us like maybe it's maybe like 2 power of n. Maybe 2. No, it's not 2 power of n. Yeah, 2 power of n.
Okay, so. That's good. It's work. But let's save speed. Is this one better or the other one better?
The other one.
Okay, they are the same.
Open the other one. It will show you how much. Click on it. It will show you how better.
So for 84 in this one.
The other one was 80. So the recursion was better.
The recursion, yes.
But both are good actually. Both are very good.
I think maybe the other solution also be.
The recursion is
but recursion was much easier and we reached much faster.
How so? It's much faster, yeah. How so? Also, what was the?
Now, if we wanna use the other technique, like add the depth with the parameter, how we can do that?
Okay.
So, for example, root is depth 1, right? So we're gonna do depth 1. So we're gonna remove counter. We're not gonna use counter. So we don't need this range here. So
it'll work with the previous version of the code.
This one. This one?
No, the one without the for loop.
Oh. This. Okay, so we can edit it here. So we remove the for loop. We remove counter because we don't need it. And instead we're gonna save it inside it. So 1 better than 1. And then somehow ish. Wait, how is that gonna work?
So, for example, you append a left, you increment the counter of the left without incrementing the other one. So each branch has its own counter.
In the queue. So a queue is gonna be like.
So now in node left, you're gonna add the other one, the other parameter that's gonna be +1. Whatever you call it, or node 1 +1.
Okay, so it's gonna be like an array of arrays. Not.
But in a queue left, you have to add the other one.
Okay, maybe we do ScaliDraw for this.
So technically, node is an array, right? The first element of that array is the actual node. The second element of that array is the depth so far of that node, right?
Okay.
So when you do queue append node, it's gonna be node 1 left because the first part of the array is the actual node. The second part is the
depth.
Yeah.
And then somehow we can get the max depth.
You keep incrementing.
You're gonna use max between node and depth. Max depth and
really, because at the end of the while loop, you're gonna have a node that has both the actual node and the max depth, and you just return the second part of the array.
Okay, guide me here. What do I do? Like, do I do another array inside?
Yes.
Okay, array root. Then this is depth 1.
Yes.
Now we're gonna keep while queue. Then
so node 1 left.
I'm gonna append another array.
Yes.
And then.
So you're gonna have to specify node 1 or node 2, node 0 or node 1. Not there.
Okay, node.
1 + 1.
1 + 1. So I'm gonna get the value of it.
Yes, but replace all the nodes with node 0.
Oh, node 0.
Oh.
Okay. We can do node 0. Is this one also not 0?
No, that one is node 1. The one is like holding the flag for the depth.
So change it in the if statement.
Not 0. Not 0. 0 and then also
node +1.
So now in your return, you're gonna return node 1. because you have it saved from the last iteration.
Node 1.
But
Yes.
you must check.
But
you must check whose depth is max between node 1 or node 0.
Yeah, because now it's gonna be a list of array, right? Like this. Our queue is gonna be like this. And the last one, for example, is gonna have depth of 3.
Yeah, because naturally the last one that's gonna be popped is the longest.
So -1? Not -1?
No, just
not,
one.
Not 1.
Because node is just an array of 2 elements.
Okay.
So -1 or 1 is technically the same.
Okay. Okay, so run. I don't understand it. Okay, I have some problem here. Closing parentheses. Yeah, didn't close this one. Run.
Yes.
I think this will the size of.
Okay, it's work. Wow, that's genius. But I still don't understand this part right here.
So
I will ask you to submit again.
So it's like.
Oh my god, this is so faster. Like 99%.
It's an array of arrays.
Because there's only one loop.
So the queue has arrays that have flags. So the second element of the queue is the flag of the depth that you are in. So when you go through it the first time, the first part of the node array is your root left. And the second part of the array is the depth flag.
Oh, because we're incrementing. The more we go down, the more we increment. So the last node we reach, it have. Okay, now I see it. Wow.
It's like you have a list that has the depth factor and the root node.
Yeah, that's amazing.
Together.
Wow. Look at this graph, bro. Like only 0.05. Okay, that's crazy.
Yeah. It's the faster one.
Wait, someone have more faster one.
Yes.
Wait, he beat 9%, even if it is 8. Is this C? C? I think it's C. Yeah.
With C will be faster, obviously.
Okay, that's a nice problem. Now, what do you think? Do we solve this one too, or we end the PLD here? I think there's still lots of people. So let me do this. Do one more and check, or I go sleep. Now react. Let me to check. Let me to go sleep. Okay, everyone want to sleep, I believe. Okay, we can end it here. It was a great session. Thank you, everyone. So next session gonna be let's see, tomorrow I believe, yes, and we're gonna see graph. Okay, it's gonna be fun. Thank you, everyone. I hope to see you tomorrow. Have a good, beautiful night.
Good night.